There's something peculiar about gravity that almost everyone misunderstands, and the misunderstanding is so deep that even when people learn the correct physics, they still think about it the wrong way. They imagine that gravity is a force that pulls things together. The Earth pulls on you, you pull on the Earth. The sun pulls on the planets. This picture seems obvious. You drop something, it falls. That's a pull, isn't it? But this intuition, as natural as it feels, obscures what gravity actually is. And when you see what it really is, the universe looks completely different. Let me start with a question. When you're standing still right now, are you accelerating? Your immediate answer is probably no. You're stationary. You're not moving. But that's wrong. You are accelerating right now, constantly at about 9.8 meters per second squared upward. The ground beneath your feet is pushing you up, accelerating you every single moment, and you can feel it. That feeling you interpret as the pull of gravity. That sensation of weight is actually the force of the ground accelerating you upward. This isn't wordplay. This is what's actually happening according to the structure of space-time itself. Now this sounds absurd. How can you be accelerating upward if you're not moving? The resolution comes from understanding what Einstein discovered about gravity. Gravity is not a force. It never was. What we call gravity is the shape of space-time, and objects moving through curved space-time simply follow the straightest possible paths through that curved geometry. When you're standing on the Earth, you're not being pulled down. You're trying to follow a straight line through space-time, which we call free fall, and the ground is in your way, pushing you off that path. Let's think about what happens when you jump off a diving board. The moment you leave the board, you feel weightless. You're in free fall. And here's the critical point. When you're in free fall, you're not accelerating according to the laws of physics. You are following a geodesic, the natural path through curved space-time. You feel no force. An accelerometer attached to your body would read exactly 0. You are, in the deepest sense, moving inertially, freely, following the geometry of the universe. It's only when you hit the water, when something interferes with your free fall, that you feel a force again. This is the opposite of what intuition tells us. We think falling is when gravity acts on us, but falling is when we're finally free from forces. Standing still is when we experience a force. The electromagnetic force of the ground's atoms pushing against our atoms, accelerating us away from the geodesic we would naturally follow. Einstein figured this out through what he called the happiest thought of his life. He imagined a man falling from a roof. The falling man would feel no gravity. If he had objects in his pockets, they would float beside him, weightless. Inside his own reference frame, he's in an inertial state, indistinguishable from floating in deep space, far from any massive objects. This was the key insight. Free fall and inertial motion are the same thing. Gravity is not a force pulling the man down. Gravity is the curvature of space-time that defines what straight-line motion means near a massive object like Earth. Now let's examine what creates this curvature, mass and energy warp space-time. The equations that describe this are Einstein's field equations, and they relate the curvature of space-time at every point to the distribution of mass and energy at that point. The mathematics is sophisticated, involving tensors and differential geometry, but the conceptual heart is simple. Matter tells space-time how to curve, and curved space-time tells matter how to move. Think of the Earth sitting in space-time. It's not pulling on anything. It's creating a curvature pattern in the four-dimensional geometry around it. Space-time near Earth is curved such that the natural paths, the geodesics, converge toward Earth's center. When you release an object, it simply begins following its geodesic through this curved geometry. To you, standing on the surface being pushed upward by the ground, it looks like the object accelerates downward. But from the object's perspective, it's doing nothing. It's coasting freely along the geometry of the universe. This explains something that confused people for centuries. Why does everything fall at the same rate? Galileo demonstrated that heavy and light objects fall together. Newton's law of gravity could account for this mathematically, but offered no deep reason for it. The gravitational mass, the property that determines how strongly gravity affects an object, exactly equals the inertial mass, the property that determines how much an object resists acceleration. Why should these be identical? In Newtonian physics, it's a remarkable coincidence. In Einstein's picture, it's inevitable. There's no force of gravity to resist. Objects simply follow space-time's geometry, and that geometry doesn't care about the object's mass. A feather and a hammer follow the same curved path. This resolves another mystery. In Newton's theory, gravity acts instantaneously across space. Change the sun's position, and Earth immediately feels a different force. But nothing can transmit information faster than light. How does the gravitational influence propagate? Einstein's answer: it doesn't have to propagate like a signal. The curvature is already there, encoded in space-time structure. When mass moves, it creates ripples in space-time curvature that propagate outward at exactly the speed of light. These are gravitational waves, predicted by Einstein's equations and detected directly just a few years ago by LIGO. Let me show you how radical this picture really is by considering what happens in orbit. The International Space Station circles the Earth every 90 minutes. The astronauts inside float weightlessly. Why? The standard answer is that they're far enough from Earth that gravity is weaker. But check the numbers. At the station's altitude of about 400 kilometers, Earth's gravitational field is only about 10% weaker than at the surface. If gravity were a force pulling them down, they should feel 90% of their normal weight. Instead, they feel nothing. The correct explanation: the astronauts are in free fall. The station and everything in it are falling toward Earth, constantly following geodesics through curved spacetime. They never hit the ground because they're also moving sideways fast enough that Earth's surface curves away beneath them at the same rate they fall. Orbit is not a balance between gravity and centrifugal force. Orbit is pure free fall along a closed geodesic path. The astronauts feel weightless for the same reason you feel weightless when you jump off a diving board. Nothing is pushing on them. They're following spacetime's natural geometry. This leads to something subtle about acceleration. In Newtonian physics, acceleration is straightforward. It's change in velocity over time, measured against absolute space. But Einstein showed there's no such thing as absolute space. There's no universal reference frame. So what does acceleration mean? Einstein's answer distinguishes two types: coordinate acceleration and proper acceleration. Coordinate acceleration is what you measure when you track an object's position changing over time in some reference frame. Proper acceleration is what an accelerometer measures, what you physically feel. The falling astronauts have coordinate acceleration toward Earth. Their trajectory curves in space, but zero proper acceleration. You standing still have zero coordinate acceleration, but upward proper acceleration from the ground pushing you. Proper acceleration is absolute in a way that velocity isn't. You can always tell whether you're accelerating properly because you feel it. An accelerometer will measure it. This is what an inertial reference frame means in relativity, a frame where test objects experience no proper acceleration, where they move along geodesics. Near Earth, a freely falling reference frame is inertial. The ground-based frame, where we spend our lives, is non-inertial. We're constantly being accelerated upward. Now let's think about what this means for the concept of gravitational force. In Newtonian mechanics, forces cause accelerations according to F equals ma. The gravitational force on you is your mass times 9.8 meters per second squared, pointing downward. But in Einstein's framework, there is no gravitational force. So where does that equation come from? It describes the proper acceleration needed to hold you stationary in the curved spacetime near Earth. The ground exerts an upward electromagnetic force on you, creating upward proper acceleration, preventing you from following your natural geodesic. The magnitude of that force is what we traditionally called your weight. This reframing affects everything. Consider the equivalence principle. Einstein's foundational insight: in a small enough region of spacetime, gravity is indistinguishable from acceleration. If you're in a windowless room, you cannot perform any local experiment that tells you whether you're on Earth's surface or in a rocket, accelerating through deep space at 9.8 meters per second squared. Both situations produce identical physics. Why? Because both involve the same thing: proper acceleration. On Earth, electromagnetic forces from the ground create that acceleration. In the rocket, electromagnetic forces from the floor do the same thing. The geometric situation is identical locally. The equivalence principle isn't just an interesting fact. It's a statement about the nature of space-time itself. It says that gravitational effects can be locally transformed away by going to a freely falling reference frame. Gravity, unlike electromagnetism or the nuclear forces, has this unique property. You can't transform away an electric field by changing reference frames, but you can transform away a gravitational field, at least locally, by entering free fall. This is only possible if gravity isn't a force at all, but rather a feature of spacetime geometry. Let's go deeper into what curved spacetime means. Spacetime is four-dimensional. three space dimensions and one time dimension, woven together into a single geometric structure. Events in space-time are points with four coordinates, where and when. Paths through space-time are called world lines. A stationary object has a world line that extends through time but not space. A moving object's world line is tilted, covering space as time passes. In flat space-time, far from any masses, geodesics are straight lines. An object at rest stays at rest, following a world line straight up through time. An object in motion continues that motion, following a tilted straight world line. This is Newton's first law, inertial motion. Near a massive object, space-time curves and geodesics are no longer straight in the usual sense. They curve. A freely falling object near Earth follows a curved world line through space-time. From our accelerated perspective on the ground, we see this as downward acceleration. But the object itself experiences no force. It's still following the straightest possible path, a geodesic through the curved geometry. The mathematics describes curvature using the metric tensor, which encodes distances and angles in spacetime. Einstein's field equations determine how mass and energy affect the metric. Solve those equations for a spherical mass like Earth, and you get the Schwarzschild metric, describing the spacetime geometry around a non-rotating spherical body. The geodesics in Schwarzschild spacetime converge toward the center. What we perceive as gravitational attraction is geodesic deviation, the convergence of nearby freefall paths in curved spacetime. This explains tidal forces properly. If you're falling feet first toward Earth, your feet are slightly closer to Earth than your head. The geodesics your feet follow converge slightly more than the geodesics your head follows. This creates a stretching effect called spaghettification near extreme masses like black holes. Tidal forces aren't a separate phenomenon from gravity. They're the manifestation of space-time curvature itself, visible when you compare geodesics at different locations. Here's where the picture gets even stranger. Time itself is affected by gravity. Clocks run at different rates depending on their position in a gravitational field, or more precisely, depending on the space-time curvature at their location. A clock on Earth's surface runs slower than a clock far from Earth. This isn't a mechanical effect or an illusion. Time genuinely passes at different rates in different parts of a gravitational field. This is gravitational time dilation, and it's been measured with extraordinary precision using atomic clocks. Why does this happen? It comes directly from the geometry of curved spacetime. In special relativity, we learned that time is relative, that moving clocks run slow. General relativity extends this clocks deep in a gravitational potential well, where spacetime is more strongly curved, runs slower than clocks higher up. The effect is real and measurable. GPS satellites must correct for this. Their clocks run faster than clocks on Earth's surface by about 45 microseconds per day because they're farther from Earth, in a region of weaker spacetime curvature. Without this correction, GPS positioning would drift by kilometers. Think about what this means. If you stand at the base of a tower and your friend stands at the top, you age more slowly than your friend. The difference is tiny for ordinary towers, but it's real and cumulative. This was verified in the Pound-Rebka experiment, where gamma rays traveling up a tower shifted frequency by exactly the amount predicted by gravitational time dilation. Time is not absolute, it's part of the geometric structure of space-time, and that structure is curved by mass. This leads to gravitational redshift. Light climbing out of a gravitational well loses energy, its frequency decreases, it becomes redder. This isn't because the photons are fighting against a force. It's because time runs differently at different heights, and frequency is a measure of time. A clock at the bottom of a tower ticks slower, so light emitted at 1 tick per second. There arrives at the top with ticks spaced farther apart in the faster time at the top. The frequency decreases. We observe this as a redshift. Now consider black holes, the most extreme consequence of general relativity. When you compress enough mass into a small enough region, space-time curves so strongly that geodesics cannot escape from within a certain boundary. This boundary is the event horizon. It's not a physical surface. It's a point of no return in space-time geometry. Cross it, and every future geodesic, every possible path through space-time, leads inward toward the singularity at the center. Not because anything pulls you in, but because the geometry of space-time itself is so warped that outward ceases to be a possible direction of travel through time. From far away, if you watch something fall toward a black hole, you see it slow down and redden as it approaches the event horizon. asymptotically freezing in time due to extreme gravitational time dilation. But from the perspective of the falling object, nothing special happens at the horizon. It crosses smoothly in finite proper time, continuing to follow its geodesic. The difference in perspectives is purely geometric, arising from how world lines are structured in severely curved spacetime. Let quotes say return to a more familiar scale and address a common confusion. People often ask, if gravity isn't a force, why do we teach F equals mg in schools? The answer is that F equals mg is not the force of gravity. It's the force required to prevent gravitational motion, to hold an object stationary in a gravitational field. That force comes from electromagnetic interactions with the ground, or a scale, or whatever supports the object. In Newtonian mechanics, we could equivalently describe this as the normal force balancing the gravitational force. In general relativity, we recognize that the normal force is what's real. It's creating proper acceleration. The gravitational force is a fictitious force that appears in non-inertial reference frames, like centrifugal force in a rotating frame. This matters for understanding motion. When you throw a ball, what path does it follow? In Newtonian physics, you'd say it follows a parabola because gravity pulls it down while it moves forward. In general relativity, the ball follows a geodesic through space-time from the moment it leaves your hand. Your throw gives it initial velocity, a tilt to its world line through space-time. Then it simply coasts along the geodesic determined by Earth's space-time curvature. The parabolic path through space is the projection of that straight path through space-time. There's no force pulling it down. The curvature of space-time is already built into what we mean by straight. This extends to planetary orbits. Earth orbits the Sun. Not because the Sun pulls on it, but because Earth follows a geodesic through the spacetime curved by the Sun's mass. That geodesic happens to be a closed ellipse in space. An orbit, from Earth's perspective, it's simply moving inertially, following the geometry. The Sun isn't doing anything to the Earth. The Sun's presence defines what the geometry is, and Earth responds to that geometry by following its natural path. What about gravitational waves? When massive objects accelerate, particularly in asymmetric ways, like two black holes spiraling together, they create ripples in spacetime curvature that propagate outward at light speed. These aren't ripples in some medium. They're oscillations in the geometry of spacetime itself. As a gravitational wave passes through you, the distances between points in space oscillate. LIGO detected this by measuring changes in the lengths of 4-kilometer-long laser interferometer arms, as gravitational waves from colliding black holes passed through Earth. The changes were incredibly small, smaller than a proton's width, but they were real distortions of space-time geometry. Detecting gravitational waves confirmed a specific prediction of general relativity, and gave us a new way to observe the universe. We can now listen to space-time itself ringing from cosmic collisions. This isn't metaphorical. Gravitational waves carry information about events we could never see with light. They let us probe the universe's geometric structure directly. Now we arrive at the deepest question: why is space-time curved by mass and energy? Einstein's field equations tell us how mass curves space-time, but they don't tell us why this relationship exists. This is where physics reaches its current boundary. We have the mathematical structure. We've tested it exhaustively. Every prediction, from Mercury's orbital precession to gravitational waves to black hole shadows, matches observation precisely. But the underlying reason why mass and spacetime are coupled this way remains mysterious. Some physicists think the answer will come from quantum gravity, a theory that unites general relativity with quantum mechanics. In quantum field theory, forces arise from particle exchanges. Electromagnetism comes from photon exchange, the strong nuclear force from gluon exchange. Perhaps gravity comes from graviton exchange, and the geometric picture is an emergent description of quantum processes. But this is speculative. We don't have a working quantum theory of gravity yet. String theory and loop quantum gravity are candidates, but neither is confirmed. What we do know is that general relativity describes gravity as geometry, and this description works extraordinarily well. At human scales, Newtonian gravity is an excellent approximation. The corrections from general relativity are tiny, but conceptually, the Newtonian picture is wrong. It's not that masses attract each other through space. It's that masses curve space-time, and objects follow that curvature. This raises philosophical questions about the nature of explanation. Have we explained gravity by describing it as space-time curvature? In one sense, yes. We've replaced the mystery of action at a distance with a local geometric framework. Objects respond only to the local geometry where they are, not to distant masses. In another sense, we've traded one mystery for another. Why does mass curve space-time? We can write equations, but the fundamental reason eludes us. This is how physics often works. We peel back layers of description, finding deeper structures, but ultimate explanations remain out of reach. Newton knew his law of gravity predicted planetary motion, but admitted he feigned no hypothesis about gravity's cause. Einstein went deeper, showing gravity as geometry, but couldn't explain why geometry and mass are related. Perhaps future physicists will find another layer, perhaps they won't. What matters is that each layer reveals more about nature's structure. Let's consider what general relativity says about the universe as a whole. If space-time can be curved locally by masses, can the entire universe have a geometry? Einstein's field equations can be applied to the universe in total, yielding cosmological models. The universe can be spatially flat, positively curved like a sphere, or negatively curved like a saddle. Current observations suggest it's very close to spatially flat, extending infinitely in all directions, at least beyond our observable horizon. The expansion of the universe, discovered by Hubble, is not galaxies moving apart through space. It's space itself, expanding, the distance between any 2 points increasing over time. This is a dynamic feature of space-time geometry on cosmic scales. The expansion can accelerate or decelerate depending on the universe's mass and energy content. We observe accelerating expansion attributed to dark energy, a component of the universe's energy content we don't yet understand. Dark energy affects space-time curvature according to Einstein's equations, but its nature is unknown. General relativity also predicts that the universe had a beginning, tracing the expansion backward. The universe was denser and hotter in the past, eventually reaching a state of infinite density and curvature called the Big Bang singularity. Whether this singularity is real or an artifact of applying general relativity beyond its valid domain is unclear. Quantum effects become important at such extremes, and we lack a quantum theory of space-time to describe them. What have we learned? Gravity is not a force pulling objects together. Gravity is the curvature of space-time created by mass and energy. Objects in freefall, the natural state of motion, follow geodesics through curved space-time. They experience no force. We standing on Earth are constantly accelerated upward by electromagnetic forces from the ground, held off our natural geodesic paths. This is why we feel weight. Time itself is affected by space-time curvature, running slower deep in gravitational wells. The universe's large-scale structure, black holes, gravitational waves, all follow from this geometric framework. The lesson extends beyond physics. Our intuitions about the world, built from everyday experience, can be fundamentally misleading. We feel gravity as a pull because we live our lives in an accelerated reference frame. We rarely experience true free fall long enough to recognize it as the natural state. Our language encodes these misunderstandings. We say objects fall down, implying motion caused by a force, when really they're simply moving freely while we're pushed up. Science corrects these intuitions by carefully examining nature, building mathematical descriptions, testing predictions. General relativity emerged not from casual observation, but from deep thought about the equivalence of gravitational and inertial mass, the constancy of light speed, the nature of acceleration. Einstein imagined scenarios, worked through their logical consequences, constructed a mathematical framework, and checked it against reality. The result transformed our understanding of space, time, and gravity. This is how we learn what's real, not by trusting intuition, but by questioning it, testing it, following logic wherever it leads. Gravity feels like a force. Our entire evolutionary history prepared us to respond to it as such. But when we look carefully, when we measure precisely, when we think clearly, we discover that nature is stranger and more beautiful than our intuitions suggested. Mass curves space-time. Objects follow that curvature. That's gravity. Everything else is just the story we tell ourselves to make sense of the acceleration we constantly experience. The universe doesn't care about our stories. It follows geometry.